Hello everyone, and this is a kind of a different video. Here we will be debugging or dry running a program. So you see, here is one of the simple program written over here, and I'm not telling you what this program is. Instead, we will dry run this one and we'll figure it out how to efficiently dry run this one, how to trace the program, and understand what the program does. So without any further delay, let's get started. So you see, first of all, we know that our starting function is combination sum. Usually these kind of programs are tough because it's a kind of recursion problem. So a function dfs calls itself multiple number of times, and hence a separate layer of call stacks add. If that was not the case, I would just go ahead, insert a table and understand what is the pointer and what's the appropriate value it gives. But now I need to trace down one by one each of the operations. So we are currently at a combination sum. We provide candidates, array list, target and whatnot elements initially. But we will just go ahead and assume few of the inputs. So we take few of the inputs as 2, 3, 5, 7, and we have a target is equal to, let's say, 7 itself. Now, in this case, what would be the result? Let's dig down deep. Now we are passing candidates to DFS. So DFS would receive in such a way. I'll just take this to a new line. DFS in a case would receive this array as A. It also takes start, sum, runner and a result array. So start initially starting with 0, which is start, sum is target, which is 7, and it also has runner, which is empty, runner, and it also has a result array. So within this, what is going on? Let's boil this down deep. So we have initial case, whether we check sum is lesser than or equal to. This we are checking frequently, so keep in mind we do not want it to have sum lesser than 0 or start exceeding beyond the length of array. Once that is done, if we check again the sum, if it is equal to 0, we store the runner, and that's it. Next we go ahead and we iterate. This is the crucial part. Once we iterate, what's going next? So once we iterate in such a way that we go ahead and again we layer down deep into next iteration. So let me take it to a better alignment now. So if we do this, now our runner is in the position of 2, as our I currently is 0, runner is 2, and now if I 0, we are calling again DFS. We are going again back to the same process where we initially invoked. We initially invoked with this kind of numbers, but now the only difference is our start is 0, sum is 7 minus 2, because we have sum minus a of I. So 7 minus 2 is 5, and hence we go with runner as 2. Still the same, we encounter this kind of loop and we go ahead with similar definition of this with a slight difference, but this time it's 5 minus 2 again, and we have 2 and 2. 5 minus 2 is 3, because we again ran the loop. We added one element to runner, which is 2 2, and we subtracted 2 from 5, which gave us 3. Similar process we are doing again. So you see how call stack is being defined over here. So we go ahead, we add runner 2, we subtract 2 from this, leaving us 1. Still, you know the drill. 1 sum as 1. Sum as 1 is not lesser than 0. Well, and neither of the start, which is 0, is greater than the length. Both are valid, so it won't end. Nor the sum is 0, it won't end. It again goes to the for loop. So within the for loop, you again have the DFS statement. So let me run the DFS statement once again, with the intention in mind to give start as 0, sum as 3 minus 2, and 1 within the runner. And now we have 3 minus 2 is, sorry, it was 1, right? So 1 minus 2, and we have 2 comma 2. Yeah, so 1 minus 2 is minus 1, and here we see that sum is lesser than 0, which means return. So while returning, we go back to this statement where we have runner as to remove the last element. We have runner to remove the last element, and hence the runner would become 2 2 2. Instead of 4 2's, we have 3 2's, and here we have sum within this line as 1. Now I for this was 0. Within the next iteration, I plus plus would, for again if I say for I plus plus, we get I is equal to 1, and if I is equal to 1, we make another call. The call is similar, but only this time we have a DFS call having the array same, which is A, and instead of start as 0, we are starting as 1. Start as 1 because I is 1, obviously, and this time we have sum. So this call is all done, so I'll just mark it as done. We are within this call. Sum initially was 1, so I'll just pass 1 minus 3, which is sum, and the rest is I'm going to add 3 within the runner, so which will make us 2 2 2 3, and hence this is runner, and we have result. Notice that nothing has been populated within the result, so it goes ahead, the call stack says it, hey, 3 minus 1, 1 minus 3 is minus 2, which is invalid, so return. Similar call will go for start for like I equals to 2, which is internal negative, 3 internal negative, and hence for 4 it's out of bound. That's the reason we are not going beyond, and we come back. So coming back is known as backtracking. So we were having 4 elements, we remove it 2, we added it 1. Now we are having 3 elements, we are again going back to remove it from 2. Our initial way is this, and here this is where we came from. Let me align it nicely. Okay, well, this is aligned nicely now. This is where we came from with I is equal to 0, but now I plus plus would give us 1. Hence our answer would be 2 2 3, and sum would be 3 minus 3, which is 0. and hence this is the first entry within the result, which is 2 2 3. Likewise, we'll go ahead and check for 2 to 5, which is not working, 2 to 7, which is not working. We are coming back to 2 and 2 itself with out of bounds, so we remove the 2. Now we are left with only 2. We see 3, so let's add 3. So 2 and 3 makes 5, so it's not yet working. Let's add 3. 5 plus 3, which is 8, which is exceeding the sum or negating the sum if we go with this logic. So it's also not working, so pop it out. Take it 7, negative, not working, so remove the 3 itself. Check a minute, wait a minute, check for 5. It's working, yeah, add the result. So the result would not only be this, but 2 5. Now if 2 5 is working, check for 2 5 5. Not working, okay, makes sense. Check for 2 7, whether it's working. No, it's not working, so go back. Wait a second, remove 2 as well. Use 3. Use 3 again. Use 3 again. Hey, what? 3 3 9. So it's exceeding the target. Remove 3. Check 5. It's exceeding the target. Check 7. It's exceeding the target. So wait a thing. Do a thing. Remove 3. Use 5 because 5 is next. It's still exceeding the target. Remove 5 and use 7. It's still exceeding the target. Remove this all. Remove 3 as well because it was giving us a lot of trouble. Check 5. 5 is good. Go ahead. Use 5 with 5. It's exceeding the target. Use 5 with 7. It's exceeding the target. Remove 5. Remove 7. Don't worry about it. And remove 5 entirely. The runner is currently empty. Check for the last element. 7. So check for 7. 7, it's working. So insert 7. Now check for 7 and 7 again. So 7 7. It's exceeding the target. No use of going forward. So now we remove 7 itself and check for any other element in the next. There is no such elements. Then this is our result array. So this is all about it. This is how you can trace an algorithm, and I'll see you in the next one.